Okay. Good morning, everyone, from here in Nigeria. Okay, good afternoon presently. This is 12:03 by my time here in Lagos, Nigeria. And I'll be introducing the presenter for today. This is Dr. Chukuma Moses Anoro. Sorry for that pronunciation. And the paper we will be presenting, the topic is modeling, the topic for the paper is the modeling and spatial characterization of aerosol at Middle East aeronaut stations. And presently, Dr. Chukuma is from the Institute of Space Earth Environmental Research in Nagoya University in Japan. May I have the honor to bring on board Dr. Anoro. So over to you.
Okay, thank you very much for the introduction. So I am Anoro. You have already mentioned my name. So I want to make this presentation on this recent paper. This the 2023 paper just got published with the Theoretical and Applied Climatology Journal. It's a Springer journal, and the impact factor is 3.4. So I also want to encourage some of the participants from Nigeria. I do understand what is really happening presently, and some of them students I know. So it's not really easy to maybe make this sacrifice of getting data loaded and also joining such a presentation. So I want to encourage them because most of us started that way. So it's always a sacrifice. So here I now start my presentation. So the title of my presentation is Modeling and Spatial Characterization of the Aerosols at Middle East Aeronaut Stations. So the journal I have introduced, the Theoretical and Applied Climatology, that is the journal that got our paper published, and I'm the correspondent and the lead author of the paper. So we have my name here, Anoro. I'm also from Nigeria, from the University of Nigeria, Nsukka. So my co-authors are here, Saeed Bukhari. Saeed is in India, and he is in the National Institute of Technology and also telecommunications in India. And then I have here, okay, Mwofo is also a professor in physics from Imo State University, Owerri. So here is my email for further discussion. And here you can see the full access of the paper if you're interested to read. So the contents, I have the abstract, introduction, the data and methods, the model we have used in getting the results, and also the station's information, and then the results and the discussion. And also we can also interact after the presentation. So starting with the abstracts, we have developed a model called AREMA. AREMA is just an autoregressive model. And we have used this AREMA to simulate AOD data from the aeronet. AOD means aerosol optical depth. I will explain as we go through the presentation. And then we have started from 2012 to 2021. We have simulated this data from 2012 to 2021 using other parameters like the precipitation, the cloud fraction, and also the Armstrong exponent. I will explain. So after this prediction, we have correlated aeronets 2021 with these predicted models from AREMA, and we obtained a coefficient of 0.9, which is very high. correlation, meaning the model predicted quite high. And then from the results of the stations we have studied, we found weighted fine mode spray for this station here. I will explain further. And then for the dust, also for Nest Diana. And then dust with maritime for the institutes in Magda. And then dust also and maritime for El Hashab station of the Aeronet network. I will explain further. So the introduction, what is this aerosols? For those not in the field of atmospheric physics or sciences. Aerosol, these are suspended particles in the atmosphere that ranges between these values, 0.009 to up to 100 micrometer. They have both the natural occurrence or maybe the man-made. This is just, if you say suspended particles, they could be solid or liquid. For example, dust. And also when there is bush burning, you also could see some soot or some particles being flare in the atmosphere. These are what we call as aerosol. So in order to characterize the aerosol from the abstract I have shown, there is a parameter called the Armstrong exponent, AE. So this Armstrong exponent is just a measure of the spectral dependence of AOD, that is the aerosol optical depth, that is continuously being applied in the ground base of Aeronet station, the satellite base, and also for modeling. This I have cited some of the previous work I have done on these studies. I could also share the PDF if we are also interested to read further and maybe understand further. Why this prediction? Now, it is very important to note, most of the times there could be instrumental issues in measurements. And also, if you have been using ground-based, there could be some sparks in data coverage. So both satellite also, if you're using satellite-based measurements, there could also be some issues. Okay, so if you're using the satellites, also there could be some breakdown in the satellite measurement. If you have used satellite data before, you could notice some 999. Those things mean no data on that particular day. So this has always resulted in difficulty in drawing conclusion in each study. So in this, we have simulated the modeling of RMA using AOD and other parameters in order to have a full data assimilation of these results. So this is the first time in the study of aerosol we have used AE to characterize, you have used RMA to characterize AE, and then it's just a time series. AE I have mentioned is just the Armstrong exponent. And the result presented has a very novel scientific result because it covers more region in the mid latitude. And also the knowledge is quite interesting because there is always a difficulty to understand the interaction between these aerosols and the formation of clouds. Aerosol also has a direct or indirect relation in cloud formation. Now, what is this RMA? So we have employed a monthly average time series, AOD, in this range, AOD, aerosol optical depth, in this visible range, 440 nanometer. According to a previous study by Reed et al. In 1999, he said AOD in this particularly visible is quite interesting to study. There are also 500, there is 600 up to 700. That is the visible range. Then Armstrong exponent also within this range, 440 to 675 nanometer. And also we have included precipitable water. All these three data we got from the level 3 version 3, level 2 version 3 of AeroNet network. And then we also included the cloud fraction from space, that is MODIS, moderate distribution of satellite. Is a satellite-based data, because AeroNet, I have said before, has AOD has interaction with formation of clouds. So it could determine if there is neat or clear rainfall in your station, in your region, depending on the interaction between that particular region with the formation of clouds. So this AOD wavelength used in this study, and also the details of the satellite-based data retrieved algorithms, I have detailed more in this study, Anoro 2021. So in the simulation of this data model we have used, I have mentioned the data we have used to train AOD, 440 nanometer, the Armstrong exponent, the precipitable water, the cloud fractions, and also identify aerosol types by setting a particular threshold to produce the Armstrong exponent results to predict future trends. This AOD has high correlation with AE. This is the Armstrong exponent. So with this Armstrong exponent, you will determine if these measured dust particles or suspended particles is dust from surface land, if it is from the maritime, that is the surface of seas, and also if it is different sources. You will see when you must have characterized Armstrong exponent, you can now say that this is what you have measured in a particular station. So this AE threshold outlined in this table, we have adopted to characterize. That's what I just said a few seconds. So the study characterization threshold for aerosol types, maritime, AOD must be less 0.3. And then the Armstrong exponent that ranges between 0.5 up to 1.7. This Armstrong exponent is just a number that ranges from 0 to 1. So dust is greater than 0.4 for AOD, and then less than 1 point for Armstrong exponent. And then urban pollution, 0.2 to 0.4, and AE, that is Armstrong exponent, is greater than 1. For biomass burning, aerosol type, AOD is greater than 0.7, and also Armstrong exponent greater than 1. So once you have maybe 1.2, and then you have greater than maybe 0.678, you now classify the characterized AE as a category or contribution of this aerosol type. So this RMR is just a Python-based task models employed from pandas. And then we have simulated these parameters, AE, CF, PW, that is Armstrong exponent, the cloud fraction, precipitable water, and AOD into this RMR. This is just the output we are looking for. And then we have used this to study this AOD in order to have the characterized using AE. And then the use of this analysis package is just a machine learning presently. So the pandas data frame is just for the identification, the estimation, and the diagnostic checking, and then the predictive results. This RMR is not just for sciences. You can use in arts, you can use in social science. Since you have a data, you can just fit in the data and then you could predict what's really the data you have studied. I will also explain further. So what is then the results of this paper? In these figures, you can see from figure 1 here, A, B, and C. For figure A, you have seen the time series frequency distribution of that AOD, the precipitable water, the Armstrong exponent, and the cloud. So simulated or fitted into RMR for this station. This station is in Iran. Now for B, you can see the time series AOD with other parameters also using the same RMR. And then we now showed in figure C the kernel density estimate for the plot. Why did we use RMR to study these stations? This station, you can see here, discontinued measurement since 2019 in Iran. This is Aeronet station. Aeronet is just a ground-based station. When we say ground-based, it's just a particular station, a particular place where there are instruments employed to measure these parameters, AOD, precipitable water, and then the Armstrong exponent. But they have discontinued this data since 2019. So that means it is not difficult to see what happens in other previous years. So we have now used this RMR to predict continuously, starting from 2019. We started from 2010, 11, 12. This is when they stopped measurements. We now continued up to 2021. So what is this kernel density estimate? It's just a non-parametric method for estimating probability density of a function. So the idea is just to approximate the probability density function of this parameter here. You can see where we have seen it is quite dense for AOD, and the model acted very well. So the frequency distribution, you can see the results for this particular station after the simulation of AOD. We got that AOD ranges higher or equal to 0.2, and then for the Armstrong exponent is greater than 1.0. From the table 1 I showed you, this is the results we got. So if you should cite table 1, you will now see that this is just a fine mode aerosol spray that is associated with bush burning in that particular station. So in this station in Iran, what really is suspended in that region is just from biomass burning. So there are quite high biomass burning in that station. So we also took some statistical results after predicting these models for that particular station. So which started from since 2010, they discontinued in 2019. So we now predicted up to 2021. So here you can see the parameters. We have just a cross correlation. So in diagonal, you can see 1, 1, 1, meaning high. When AOD correlates with AOD, it should be 1. So once they correlate with each other, you see just a perfect correlation. But quite interesting to see the real correlation between the model, maybe precipitable water with AOD, is quite high. And also AOD with Armstrong exponent has a negative high correlation. Now this RMR I have explained is just a time series modeling, very flexible, and you can use. So it's just studies the seasonal patterns using autocorrelation and partial autocorrelation function. So the stations we have selected shows a very clear distribution for that AOD study. And I have stated in the abstract that we didn't just conclude after predicting AOD, but we also tested the validity of this RMA by correlating error rates that we got in 2021. This station has a very quite missing gap, 999. When you download, if you're familiar with data, you could see some stations, some numbers, 999, 999. That means missing gap. But this station, there was up to, in the months April, May, and June, just these three, for 2021, there was some data. So we now included this Aeronet station fitted with RMA. We got a value 0.9 correlation, meaning the model performs quite high. And also for the MODIS, which is also a satellite base, we got a quite interesting correlation up to 0.5, meaning also that the model predicted very well. Now for this station in Israel, that is the Nez Ziona, I have explained the frequency distribution, the time series, and then the Cannet density. This particular station discontinued since 2015. So it's difficult to see what happens since after that 2015. They operated in 2009 to 2015, and they stopped measuring or measurements of these parameters. Then we have continued using AREMA to simulate this. AREMA studies this. That is when you say autoregression, is just using the past values to predict the new values. So we have used this 2009, 11, 12, this is 9, 10, 11, 12, 13, 14, 15 to predict. We have studied this and then we simulated from 15, 16, 17, 18 up to 2021. So for this station, is just located in the coastal plain in the Mediterranean Sea. So what was the result? The result shows these values for AOD greater than 0.2, and for AE, that is the Armstrong exponent, less than 1. Using the same table, because the table, once you have these results, you go to the table and see what category is your results. So we also see that there was a significant contribution of dust in that station. So for this Israel station, the aerosol, that is the suspended particles in that region, is quite dust. Maybe it is also a contribution from the Sahara. There could also be a factor. Now for this station in United Emirates, we have also this station has several missing data. This also presently active, but there are several missing data measurements since 2009. So very difficult to understand or maybe draw conclusion on what is really happening. When you have a sparse data, it is difficult to study, and then see what is really happening. Maybe, for example, you have a number 1 and everything misses and up to a number 10. It is difficult for you to see what is the progression of that number. Are you trying to say maybe counting 1 to 10, or maybe counting 1, or maybe odd or even number from 1 to 10? So it's very difficult to draw conclusions when there is spaced data. Now for this particular station, we have seen these results for AOD greater 0.4, and then for the Armstrong exponent is between 0.5 and less than 1. And then the cloud fraction greater 0.7. And then we see that dust and the maritime aerosols are likely the background aerosol in that particular region. So this is good to understand the microphysical properties of that aerosol in that particular region. Like I have said before, that the aerosol also have direct and indirect relationship with cloud fraction. So here you see that meteorological precipitable water cycles also we have investigated, and we got these values 0.52, which is quite high. So aerosol also, this time people normally say about the climate change when there's a particular month when we are not expecting rainy season, but suddenly you start seeing rainy season, or maybe start seeing rain. And also there could be a particular month when it should be dry and you now start to see also rain. This is a parameter which is the suspension of particles that do determine that. So for dust aerosols, they are quite driven by advection. For example, if you live in the tropical of Nigeria, you see those in the north are quite facing the Sahara, and then there are a lot of dust particles in that region. That is coming from advection, which is the wind that is projecting those dust into the town or region located in the far north. So this also has a very clear microphysical interaction with the formation of cloud. The north, you can see, they do experience extreme weather. When it is raining, extreme, and when it is harmattan, extreme. So this is as a result of the meteorology in those particular regions. Now we also show the statistical results of this next Zayana from 2009 to 21. This we show, I have explained, showing the results of the statistics, because statistics is also the heart of every study. Once you have a study, you try to correlate to see what's your data, if it is quite interesting or if it is not interesting. So in these tables, we have also presented the statistics of those parameters. Statistics is just is a multidisciplinary will I say parameter to use correlation, and then is quite there is a way also to interpret when a number ranges between 0 and 0.2, from that 0.4 and then up to 1, which is a perfect correlation. Now for this table 5 shows for this station, that is the regression that denoted a moderate inverse relationship indicating a coupling. What I mean by coupling here is the interaction between the aerosol and the cloud formation. So aerosol has a very high determination or deterministic property on a particular station, on the meteorology of that station or region. So this station in Saudi Arabia, this is Ada Eksham. This station could discontinue since 2014. There. So difficult to see. They started in the year 2012, and in 2014 they shut down the station. So what now happens to maybe science in that particular area region? Difficult to study. So RMR has helped to continue generating this data up to the year 2021. So to characterize the distribution of this aerosol at this particular station, we got these values. and we see that dust aerosol is what dominates in that region. So in conclusion, we have analyzed quite well the aerosol and the interaction with the clouds over the area. Like I said in the beginning, this is just the very first time in this study, this particular results is coming out. So for the comprehensive statistical modeling of aerosol, using AOD in this particular value, which is the infrared 440 nanometer, we have characterized using Armstrong exponents based on the surface-based aeronet network covering approximately 2012 to 2021 period. So the results, this is a continuation. This study is a continuation of my paper in 2021, where I have studied this particular station. And also I have observed the applicability of RMR time series, because when I studied this station in 2021, after simulating RMR, I also went back to compare the results I have here. And then I see and concluded that RMR is feasible to predict AOD using the statistical modeling of auto-regression and regression analysis. So here we have used the past months, like I have said, to predict the mean time series aeronet network. So the basic thing or the results is quite interesting, and it is now nice or good for those people in aerosol science that is making use of those data. So we have here the data now present. So, and also we have concluded that it is quite nice for those stations to continue measurements, because our data has only stopped in 2021. So what happens now here, now is 2023, meaning if we are located in that region, you cannot continue study in your of aerosol or suspended particles in your region. So very difficult. So this relationship differs from one station to another, which is the results. We have some stations being dominated by dust, maritime dust, and some stations by biomass burning. So, and we have concluded that this aerosol distribution has a strong meteorological influence. So in general, the results has studied quite well the stations in the Middle East. And we concluded in general that dust aerosol dominates, and this has a very high influence to determine the meteorology of every region. So that's my presentation. And in this paper, I have highlighted, in this figure, I have highlighted the base study, the 2021 study, which I have published in Urban Climates in 2021. So if you're also interested to read further, after this study, I now decided to use RMR to predict AOD. And then I compared results obtained from this study. I didn't use model in this study. Then when I use model in this present study, I now compared the particular station results with this. And I found that RMR is quite interesting to study meteorological data. Thank you for listening, and I'm open for further discussion.
Wow. Thank you very much, Dr. Chukuma Anoro. That was a nice one. Well done. And that was really a good presentation. Well done. And thank you for your time. And I believe several people might have questions or question for him. Please, if you have a question, kindly use your electronic hand to signify, so that I can give you chance to speak or to
Dr.
ask
Aneyo,
question.
I have a question.
Yes. Okay. But okay. So any other person? Maybe I should just gather people, the different people that have questions.
I think we can just ask
We
our
have
questions.
any
So,
as it okay. Okay. You can go ahead, ma.
so Dr. Nuro, thank you so much
Yeah.
for that very informative presentation.
Okay, thank you very much.
I think I learned a lot from it, and I'm just knowing about the ARIMA model that you talked about.
Hmm.
So I'm also interested, and I would like to also use it for. I believe that you can use that. Can you use that model for other kind of studies apart
Yeah.
from aerosols or air studies?
Yeah,
Okay.
you can use
So
in every study. Yes.
oh, that's good. Okay.
Hmm.
So I want to know the level of accuracy. That is one, because from what you said, the data depends on some of this data depends on environmental factors, because you said
Hmm.
dust, and we have issues of climate change. So what happens in year 2020 may not happen in 2021.
Hmm.
So how is this model able to predict accurately? I'm just wondering. Then can you use this model to, okay, you can't use it to predict past data, or can you? That's another question I have. Assuming you have data for 2019, can you use that model to predict, no, not predict, but just, determine what the data was maybe years back? So that is my third question. Then the fourth question is for seasonal patterns. For somebody like me, we sometimes in our work, environmental toxicology, we collect data for maybe wet season, dry season. So is ARIMA a model that we can use even in our study? Maybe when we are collecting data for water quality parameters for different rivers, for example. So can we use ARIMA to now predict? We know that in this part of the world, it's very expensive collecting data. So this model will be very good if we understand how to use it. If we understand how to use it, because collecting data in this part of the world is quite expensive. So if we know how to use this, your model, it will go a long way in helping to, some of the pollution problems that we have. So those are the questions I have.
Okay, if I got your question accurately, you said first question, you said if really, what is the accuracy of ARIMA? Now,
level of accuracy, yes.
Yeah, the level of accuracy is, I have shown in the presentation. I am trying to share the slide, but I'm just seeing blank. I don't know why. So, but in the presentation, I have shown that we, after predicting this using ARIMA to simulate this AOD data, we also correlated this Euronet data with ARIMA predicted in the year 2021, and the correlation quite high, 0.9. So it is quite high. The accuracy is quite high. It is good to predict. And also in the figures, you can see this in the pattern of the already existing data on those particular stations. And then it followed also the same pattern with the predicted. So the accuracy high. Now the question again is about meteorological influence. You asked about meteorological influence of those.
Like climatic influence.
Yeah, the climatical influence. Yeah, the climatic influence, there could be some climatological influence in a particular data. But ARIMA uses auto-regression. This auto-regression is just to use the past existing to predict the future. So ARIMA studies also what happens on those particular seasons, and also give out an output, which is also very correct. Now, also the third question is if really you can do a backwards trajectory of that data. Maybe you have maybe I could, for example, I have started from the station that stopped in 2014 and then predicted up to 2019. Yes, this is what we call the forward modeling. RMA also, I can use it for backward. I can also predict, had it been that this station was here in the year 2010 or 29 or even the year 1999, this is what the measurement code would have looked like. So I could also use RMA to do the backward trajectory to see the results of those particular stations. So
Thank you very much.
The fourth question, I missed the fourth question. Could you just maybe remind me?
That is using
Okay, I said,
secondary
for
data.
example, that for my field, that we collect data sometimes on water quality parameters for different rivers. And we do that seasonally. That is it possible to use this ARIMA model for that kind of study?
Yes, yes, it's quite possible,
Okay.
yes.
Okay, so for those of us who are interested in this ARIMA model, how do we learn how to use it? Is it a software or is it accessible or is it a paid software?
Python is an open access high level language program. So it is not like MATLAB that is difficult to access. So Python is open, and then maybe if someone that has the knowledge of programming, so could possibly, what the person needs is just maybe someone to give, maybe this is what you employ in the stacks model in order to use RMA for predicting your data.
Okay. So finally, are you open for collaboration? Because I'd like to collaborate with you in this particular model.
Yeah.
Are you open to collaboration? To collaborate?
Yes, I am open.
Okay.
There is a question in the chat. I want to ask the presenter that how can we describe aerosol that is always present in paper?
And the yes, paper markets. Yeah.
Is it dust or biomass? Or can we say it is liquid aerosol? Yeah, the question is you have these paper markets. If you have the measurements in this paper market, you cannot characterize the data using the Armstrong exponent. So the table I showed, the data I showed in that table one, once your AE falls in that particular range, it will help you to classify that this is dust or maybe this is liquid or maybe from biomass also. Did you hear me?
Hello, Deborah. Does that answer the question? Okay, thank you. She said where she is noisy. Okay. Any other question? Do we have anyone who wants to ask question? Okay, but my own question, it's just a follow-up question to what Dr. Duarte asked, is that can we use a secondary data for this kind of model? You know, extrapolating data from past work, from past papers, like a secondary data, or it must be original?
No, you can use any data. What RMA does is just to study the data you have. Maybe you showed me, unlike you are teaching a child how to read 1, 2, 3, something like that, or A, B, C, D. You know, someday the child will now be a professional in reading A to Z perfectly. So what RMA is, just you give RMA some numbers to study. And then you now ask the RMA to give me these numbers back, but making it more further.
Okay.
Yeah, maybe you counted 1, 2, 3, 4 to 5. And then you give RMA a number starting from 1 to 5. Arima will look at this number 1 to 5. And then you come back to Arima and tell me, I want a number 7. Give me number 7. He will go back, or it will go back to that number starting. Oh, you have counted 1, 2, 3, 4, meaning after 5 is 6, and after 6 is 7. It gives you the 7th number.
Wow. Okay, thank you very much. Do you have any other thing to tell the house, or do we have any? Yes.
Oh, no, nothing to.
Okay, but we are open to collaboration. So I believe several people want to collaborate with you. Maybe just in a minute, you can just send your email address to the platform, or means to which people can contact you, so that we can further the conversation via email, possibly. And I want to thank you for your time. I know it's not easy. It's very late over there in Japan.
Yeah,
thank you
for
your time. Yes. And also for the participants, thank you very much for joining. Thank you for the sacrifice. And hope to see you soon next month in another presentation. Thank you.
Right,
So we come to the end of today's review, and we appreciate you all. Thanks.
Thank you, Dr.
Thank you.
Anoro. Please, I'll keep in touch so that we can talk more on this.
Okay.
All right. Thank you.
Thank you.
Okay, bye.
Bye.